Let us continue the discussion about the k-nearest neighbor. In the case that when we try to use the Euclidean distance through the simple cases, and that can solve a lot of problems. However, what if the data set is no longer looks like what we were used to see? Saying that we are looking at a categorical data for the values, or we are looking at some binary data sets over here. So I want to move our k-nearest neighbor discussion into a real application that in my research that works on, which is working on some binary data set. And that's the kind of data set we want to discuss first. And then we will move into how do we target this kind of data set for category style of the values. So starting with the wine data set, this is kind of the formats that we are looking. We may have multiple wines over here, saying that we have two wines, and these are like the characteristics to describe the wine. So in this case, wine 1 has the cherry flavor, chewy tannins, as well as the beauty to describe the style of the wine. However, in the wine 2, we only have beauty over here. So saying that we want to calculate the distance between the two wines, how can we do that? Of course, we can simply using saying the Euclidean distance or Manhattan distance, which is like city block distance, just simply subtract the values. So 1 minus 0 gets 1, 1 minus 0 gets another 1, and 1 minus 1 is equal to 0. So the distance of this equals to 2. We can totally do that. However, I'm going to show you a real world scenario to let you know that that is probably not the best way of doing so. So in the IEEE data port, it is able to download the data set I'm looking at in the next slide, so that I'm just showing you that in some real world scenarios, once you download the file, you will see a data looks like this. And of course, this is just a very small portion of the shot for the data that I'm using. So in this case, we have thousands of wines over here. And now we have multiple attributes. In this case, we have close to 1,000 attributes. One thing you will notice is that this is what we call a sparse binary data set. The reason I'm going sparse is because most of the values are 0. And therefore, you can see that we have some single ones over here, and most of the values are 0 because there's a lot of attributes, and a wine can, in our calculation, a wine is averagely having like 10 attributes to 20 or like 30 at maximum. So of course there's a lot of zeros over there. And therefore, if you consider this 0 and 0 for two wines that we want to do the comparison, saying that this wine number 23 and wine number 24, there's a lot of zeros over there already. So the distance between 0 and 0 are like common. There's nothing surprise. And when you have a 1 and 0 over here, indicating that this is some differences that you want to put into consideration. Of course, if you have a 1 and 1 occurs on the same attribute for two wines, that's something very special, in especially the sparse data set that we are looking at. So we want to put more credit on those kind of positive attributes occurs together, while we don't want to consider 0 and 0 as something important that we want to pay attention to. And therefore, the idea of Euclidean distance does not work in the space of what we call a binary data set. So how can we really calculate the distance between the two values? There's, again, of course, a lot of different ways, and actually I will also show you some alternatives. But in my research, we found out that Jacquard's value, Jacquard's coefficient, or Jacquard's distance are actually pretty useful. And they are actually the same thing, even though the formula looks slightly different. But while we look into the calculation, you will understand why they are the same thing. So let's focus on Jacquard's coefficient. It equals to P over P plus Q plus R. And this can be very easily understood through the descriptions of each variables over here. P indicates the number of variable positive for both objects. So if that's 1 and 1, then we consider that as a p-value. So we want to look into among all, say, 10 attributes, how many of those attributes occur 1 and 1 for both items? If there is 2 of those, then P equals to 2. If there are 3 of those, then P equals to 3. And P, of course, is something that we want to focus on, and so that we will be able to see that if that is something occurs on both items that we are interested in. Q is indicating for variable positive in one item but not on the other. So saying that we are comparing y1 and y2, the attributes occurs in y1 and that's a 1 but a 0 on y2, and that is the Q value that we are looking at. So we want to see how many of those cases happening. And on the other side, number of variables positive in R but not Q, then that is another value that we are interested in. So you can see the Jaccard's coefficient is simply P over P plus Q plus R. And you can understand that we totally ignore those values are both zeros in both lines. And therefore, this is what we call a Jaccard's coefficient. On the other side, Jaccard's distance equals to Q plus R over P plus Q plus R. So you can see that the two values, if we sum up Jaccard's coefficient and Jaccard's distance, is always equals to 1. And therefore, they are actually talking about the same thing. In this slide, I want to focus on Jaccard's coefficient, and basically, you will just understand Jaccard's distance is something alternative, but it's actually the same thing. And you need to also need to understand Jaccard's coefficient. When it equals to 1, that means it's the maximum similarity. So that's Jaccard's coefficient's maximum value. On the other side, if Jaccard's distance equals to 1, that means they are totally different from each other. Because you can understand distance indicating that the shorter the better, the coefficient indicating the higher the better. So you just need to understand for the Jaccard's coefficient, when it equals to 1, that means the two things are identical. So let's take a look at an example here. Saying that I have only, of course, this is a much simplified example to go over, make sure you understand about it. So saying that we have two y's that we want to do the comparison, and then saying that we have 3 attributes, that's what we are putting into considerations only, just like the examples that we see earlier. And you can see that among all of the 3 attributes, there is one value that are presenting 1 for both y's. So the distance, when we calculate the distance between y1 and y2, P equals to 1 because there's one attribute that occurs positive for both y. Q indicating that when we compare with y1 with y2, how many of those attributes are positive in y1 and not positive or negative on y2. So you can see that the 2 red lines is representing the ideas over here. So we have 2 attributes that occurs on y1 but not on y2. And of course you can see that it's not considered over here because the P is already pick up these values already. For R equals to 0 because for y2 there's only one attribute as 1, but that is covered by P already. And there is no attributes in y2 that are positive and negative for y1. So we can see that the R is 0. Therefore, when we try to calculate the Jaccard's coefficient, it's equals to P, which is 1 over P plus Q plus R, and then it gives you the value of 0.33. So that is the idea of how you can calculate the coefficient in the binary data sets. And that is something I want you guys to understand and be able to adopt into the k-nearest neighbor problem. And therefore, this is the assignment that I want you guys to do. So saying that for the training data set that we have 6 y's as our training data set, and we try to predict the score is going to be 90 plus or 90 minus. Of course, in the world of y testing, 90 plus y's are indicating they are either classic or outstanding y's that you want to buy or interested in. So we have 6 y's over here. 3 of them are positive case, 3 of them are negative case, and these are their attributes representing in each y over there. So now I have an unknown y comes in. So I don't know this y is a 90 plus or a 90 minus. So I want you guys to use the k nearest neighbor and then calculating the distance through the Jaccard's coefficient. Again, remember Jaccard's coefficient, the higher the better. So if you can find a Jaccard's coefficient for unknown y with the testing data y that has a Jaccard's coefficient equals to 1, that means they are identical and they are exactly the same, and of course that would be your closest neighbor. But in this case, I don't think in these examples we have that case. So you need to pick up some higher values, and then I want you to use k equals to 1 first to make a prediction. Tell me this unknown y is a 90 plus or 90 minus, and then when it comes to k equal to 3, so you need to find 3 closest neighbors and then make the prediction. K equals to 5, do the same thing to make the prediction. Also notice that there might be a tie because we are looking at some very simplified table over here. So when there is a tie, how would you break the tie? What is your tiebreaker mechanism over there? So I want you guys to put some thinkings doing this assignment carefully, and then tell me what is the predictions when k equals to 1, k equals to 3, and k equals to 5, and why is that? Tell me the reasons, and also provide me all the necessary calculations. So I want to make sure that you really understand not only the k nearest neighbor algorithm, but also the Jaccard's coefficient distance calculation. So on top of Jaccard's coefficient, the things that I have mentioned to you, there are actually many other possibilities of calculating the binary distances. So based on what we have seen earlier, P is actually in this slide represented as S11. So this is probably even easier to understand when the attribute that occurs in both items or both y's that you are looking at, that's what we call S11, which is P. S10 means 1 is attribute, positive attribute on one, and on the second y is 0, that is the value of Q, and S01 is indicating the R value that we were looking at. In this slide, they also, unlike Jaccard's coefficient or Jaccard's distance, there are some other calculations also interested in S00. That means they are both zeros on both sides. So in our previous slides, we actually have not talked about this case, but now you can see that the tables over here is representing all possibilities of the binary data set calculation distances. So the first one is Jaccard's distance or Jaccard's coefficient that we have mentioned, S11, which is P over P plus Q plus R. So this is something that we exactly the same thing that we discussed earlier. There's another one called dice. Dice is very similar. The only difference is that it added 2, so it tried to give a little bit more variations on the S11 items that we are most interested in, and therefore this is another calculation. Correlation is something that probably looks most complicated, but it actually generates very good results in my research. This is something that actually put into considerations of S00 over here. So you can see that it's much more complicated in terms of the calculation, but since it add the information of S00, it's actually generating pretty good results. The rest part of it is like your Russell and many other things. There are some variations of what we have done earlier, but you can see that there's all possible choices that you can make in the binary data set. And this is only in the world of binary data set, not to mention that in the world of the numerical values, there's so many different kind of choices that you can have. And this is just something I want to let you guys know. K-nearest neighbor, the algorithm itself is very easy. But when you put that into real implementation, there's a lot of variation, there's a lot of choices that you can make to, say, improve your results. So finally, coming back to the categorical data that we were looking at, and I want to discuss this a little bit with you guys as well. So saying that, come back to our old sample examples, we have prediction, try to make prediction of a person is going to buy a computer or not, so that we use this as our labels to make our predictions. And in the data sample, saying that we have a person age is greater than 30 years old, income equals to low, student yes, credit rating equal to excellent. You can see that in this binary data, in this data set, some of the attributes are binary already. So you can see student is binary data set, credit rating is binary data set. Age has 3 categories, while the examples that we are looking at is actually covering 2 areas, because age greater than 30 covers 31 to 40 and greater than 40. So of course we can convert, and this is part of the data pre-processing part, we can convert that into the binary data set as one of the approach to tackle these problems. And for the income, it can be low, medium, and high. So how we can totally change low is equals to one category, medium and high to another category in terms of reflecting the testing data that we have. So you can see that when the testing data set that we're trying to do, this is the values, we can totally convert that into binary data. Age greater than 30, we can make that as a 1. Income equal to low, we can make that as a 0. Student yes, credit rating excellent. And then it's saying that I want to calculate the distance from our very first training data set, which is the one that shows over here. Age less than equal to 30, high, not a student, and fair rating. This is actually a total opposite of the data set that we have. So if we list all of things out, you can see that the 2 values are actually very different from one another. And therefore, you can see that when we try to calculate P, there's no attributes that occur on both sides, and therefore it's 0. Q, for testing data, it has 3 ones, that on the training data they are 0, and on the other side R, there's one attribute as a 1 and then 0 in the testing data, so that if we try to calculate the Jaccard's coefficient, you can see that the value equals to 0. Since P equal to 0, you basically don't need to care about anything else, because it will 0 over anything is still 0. So if we take a look of the example with the 5th training data set, it will generate something slightly different. So if we take a look of that, the testing data set is 1011, while the 5th training data set, age is greater than 40. As we mentioned, we try to convert that as a 1 over here, because it satisfies, it covers the data. It's part of the data over here. And income equals to low, so it's a 0. Student yes, it's a 1. The only difference is that the credit rating is fair, so this is a 0 over here. While we try to calculate the PQ and R for Jaccard's coefficient, you see that there's one attribute that occurs on both sides, there's another attribute occurs on both sides, so we will P will equal to 2, and then for Q, there's only one attribute that's positive over here and 0 over there, so we have a 1 over here. And for R, it's a 0 because there are 2 positive cases, but they are covered in P already. And therefore, while we have all the PQ and R, we can calculate the Jaccard's coefficient for the 2 samples that we are looking at is actually 0.66. So that covers the ideas of the binary data set and applied into the k-nearest neighbor. And this is basically what I want to discuss with you guys in the k-nearest neighbor topic.